Hello students, good morning everyone. This is Sekhar from M Sigma Gokulam. I am Sekhar, a senior most faculty in GATE across India, having an experience of more than 25 years. My dear GATE aspirants, the D-Day is fast approaching. Another 12 days approximately. February 3rd we have the exam for mechanical. My dear mechanical students, the main idea of today's video session is just to make use of the last 12 days of GATE preparation, or rather we have the D-Day 12 days away. What to do in these last 12 days? What not to do? Actually, that is the main intention of this video, because in the last 1 year, almost more than 1 year, some aspirants more than 1 year, you have been eagerly waiting to write this GATE examination, undergoing vigorous GATE coaching, maybe across various coaching institutes. So, having almost completed the coaching, how to revise in these last 12 days, how to re-revise, or rather how to how to fix your program in these last 12 days, so that there are certain areas of the GATE syllabus which are definitely being asked. In those areas you have to give a more focus. The idea of this video is to make you understand what to do in these 12 days, so that in these 12 days you would be able to revisit or re-revise those particular topics which are most importantly asked, damn surely being asked in this upcoming GATE examination. I am going to touch those other topics where in each subject, now most of the subjects actually which I am quite aware of, and considering my vast experience. First, I consider the heat transfer. The weightage of this subject, as you have seen, is 8 marks. In GATE 22, it went up to the more than 10 marks. In the last before year, it gives more than 10 marks. So that was the weightage given to this. If you just look at this heat transfer, we know that there are 4 chapters: conduction, convection, radiation, and heat exchangers. If we just look at this conduction, slightly bigger topic, where the most important topic that may be asked is critical radius of insulation. Critical radius of insulation. That is one of the very most sought after topics. Whenever you told that, we know well aware that critical radius of insulation is given by K by H. So whenever you are doing this problem of critical radius, just after solving the problem, just after calculating the critical radius of insulation, draw this graph. Based on this graph, try to decide the final answer. Okay. First, evaluate the critical radius of insulation from this formula, and then draw this graph and put the given dimensions in the figure, and then try to decide. Most of the situations you will be given the initial radius at this location. Then what would happen? Whether heat transfer rate will increase or decrease? That is the most probable question that may be asked. So this is one area where you may expect the definitely questions there. But generally, how to identify that question, you may think of that. Just that radius of the wire will be very thin. In the critical radius problems, you observe that the radius of the wire will be around 5 mm or 2 mm or 3 mm like that. You can easily judge that. But this is only for the cylindrical. And if it is a sphere, it is 2K by H. If it is a sphere, it is 2K by H. This is one important favorite topic that is being asked. Another thing is a composite slab subjected to the maybe convection on both sides. This is a convection. This is a temperature of the fluid, and this is a temperature of the cold fluid, hot fluid and cold fluid, and you may be given this temperature of the gas and temperature of the fluid, and the heat transfer is happening. So the temperature may be given at the interface and the fluid, may be given at this point and at this location. We don't know. The temperatures may be given at any location. So that sometimes the gas temperature may be given, sometimes this surface temperature may be given, sometimes the interface, sometimes. So 2 temperatures will be usually definitely be given, 2 temperatures. So where are they? That may be varying from problem to problem. Supposing if you had given this temperature here, say for example, this is T1 and this is T infinity, then we have to consider the thermal circuit. Thermal circuit is the main heart of these composite slab problems. Okay, thermal circuit, you have to be very thorough with the thermal circuit, wherein we have come across the two resistances, conduction resistance and convection resistance. For the slab, what is the conduction resistance? B upon Ka. For the convection resistance, what is that? 1 upon Ha. So just put up those convection resistance and conduction resistance by considering the appropriate given temperatures in the problem. Supposing in the problem we had given this temperature and this temperature, then how many resistances will be there between T1 and T infinity? There is one conduction resistance and again there is a convection resistance, considering this as the direction of the heat flow. This is one of the very most commonest models that is usually being asked in the gate examination. But supposing if you had given this temperature and this, then how many resistances will be there? One conduction, another second conduction and again convection. Okay, conduction resistance we know, that is supposing B upon Ka, and convection resistance is 1 upon Ha. If you take this one, this is T1 and T infinity, between this and this location. Supposing if you take between this temperature and this temperature, there will be three resistances, one conduction, conduction and again convection. Supposing if you take between this and this, there will be 4 resistances, both sides convection, in between conduction. So what are the temperatures you are selecting for drawing thermal circuit and what are the thermal resistances existing between them? So that is the most common problem that might be asked there. And coming to this composite cylinder, this is also very routinely being asked. Actually in the GAT 22 also has asked the polyvinyl chloride problem. Actually supposing if this is a composite cylinder, that may be expected more commonly. If this is a radial heat transfer, we have the conduction resistance offered by the inner material and the conduction resistance offered by the outer material. So what is the how many resistances will be there between this T1 and T2? Please note that T1 and T2 are the temperatures of the solid surfaces. What is the conduction resistances? We have to consider ln R2 by R1 divided by 2 pi K1L, and the second resistance will be ln R3 by R2 divided by 2 pi K2L. Okay, 2 pi. This is how we need to calculate the radial conduction heat transfer if you are dealing with a composite cylinder. This situation is called as a composite cylinder. Okay, sometimes we don't know. Sometimes there may, in the GATE 22 question, what he has asked is he has given just a bare cylinder. Just a bare cylinder, a bare solid cylinder, there is a fluid is there. Definitely between the surface of the cylinder and the fluid, there is a convection happening. What is the convection thermal resistance there? What is the convection thermal resistance? 1 upon Ha. This is the convection thermal resistance between the surface and the fluid. Okay. So the situation may change. The problem you have to thoroughly understand, particularly in the first chapter of conduction. What are the temperatures given and where are those temperatures in the given geometry? So supposing if you just take this temperature given and this temperature given, there is only one resistance. Supposing if it is lagged with insulation, if it is lagged with some insulation, supposing if this is the lagged with some insulation is there or covered, between this location and this location, how many resistances will be there against the radial heat transfer? There will be 2. What are the 2? What is the conduction resistance here and what is the convection resistance? So we have to wisely select the locations of the temperatures given in the problem by drawing the geometry on the rough paper. We will be given the rough paper in the exam. So, and locate those temperatures and what are the resistances existing between those two given temperatures. One resistance may be conduction, another may be resistance may be convection. Sometimes only 2 conductions will be there. For example, in the previous situation, if you just look at the previous situation, if you had given this and this, how many resistances will be there? Only conductions will be there. Okay. But in this case, supposing if you are given this one and this one, only 2 conduction resistances, one is offered by this material and the other offered by the other outer material. So that particular kind of a precaution we should always consider. Okay. Then the most important topic other than this that will be asked is the heat generation. Heat generation is recently in the recent GATE examination, very commonly it is being asked, particularly heat generation in slab is asking. Actually 3 geometries are there, slab, cylinder and sphere. Heat generation could happen in any of these 3 geometries, but most commonly is asking in the slab cases. In the slab cases, very commonly it is being asked in the slab cases where uniform heat generation is assumed. Uniform heat generation, Q dot watt per meter cube. Okay, in gate 22 is again non-uniform heat generation is asked, but that is one of the rare questions that is generally expected. Gate 22, if you see, there is a non-uniform heat generation. Heat generation is there, but that is non-uniform. That means different locations, different amount of heat is generated. But this is if you just think as a uniform heat generation, any kind of a situation may prevail. A symmetric parabola, in case if both sides of the slab are at the same temperature, or sometimes it may be unsymmetric parabola like this, in case this temperature is more than this. While in another case where one side of the slab is completely insulated, you may have this kind of a temperature profile, but all the temperature profiles are parabolic. Please remember that whenever there is a heat generation problem, you are doing, the most important boundary condition that should be kept in the mind is the total heat generated in the entire body should be equal to the heat convected from the surface of the body to the fluid. Please keep remember that the total heat generated in the entire body, entire slab, and that shape of the body could be anything, maybe slab or a cylinder or a sphere. The total heat generated in the entire body should be equal to the heat convected to the surrounding fluid. Then only the steady state conditions can be maintained. This is a very most important boundary condition we have to keep in mind, based on which there is a question asked in the recent gate also. Actually, the situation was like that. There is a 3 slabs here given, only the heat generation in the center slab. These 2 slabs are not generating heat, but there is a convection happening from the 2 sides. So how do you write the energy balance? Heat generated only in this central slab, total heat generated, should be equal to the heat convected from left side plus heat convected from right side. There is no heat generation in these 2, but if you take the whole combined 3 slabs put together as the control volume, for the steady state situation, this heat, because heat generated is there only in the central part, this total heat generated should be equal to the heat convected here from the right side plus heat convected from the left side. This kind of a energy balance we have to consider, particularly whenever you deal with the heat generation inside a slab. Mind that if the one side of this slab is completely insulated, at that location obviously we are obviously getting the maximum temperature. Generally what they ask is, in the heat generation cases, where do you observe the maximum temperature and how much will be the maximum temperature? That is the very commonly expected question. Where you would see the maximum temperature and how much would be that maximum heat, how much will be the maximum temperature? Where do you would see the maximum temperature? Where will you see? At what location within the slab you see? Supposing if it is a both sides the temperatures are same, you will see definitely you will see the maximum temperature at the mid plane where there is a symmetric parabola. If it is a unsymmetric parabola where these 2 temperatures are different, you will see the maximum temperature in that location of the part of the slab where you are observing more temperature. So this surface is this is T1 is more than T2. You will see the maximum temperature in that portion of the slab which is closer to that higher temperature. But this is an unsymmetric parabola. If it is a one side of the slab is insulated, then this is also parabola, but maximum temperature you will see at that insulated surface. So these are the important cases you need to remember that. Okay, this is a very important case. You may expect the question, but all the questions are solved from this differential equation only. D square T by dx square plus q dot by k is equal to, this is a beginning point for steady state one-dimensional heat conduction with uniform heat generation. This is the beginning, this is the starting equation. D square T by dx, one-dimensional steady state uniform heat generation. In gate 22 has asked the non-uniform heat generation, that is this q dot itself has become a function of x. Q dot itself is a function of x. That is an unusual question, but he has asked in gate 22. So you should be ready for any kind of the problem. But when you integrate that, you will get 2 constants of integration, because this is a second order differential equation. Those 2 constants of integration must be wisely evaluated from the given boundary conditions. Boundary condition, what do you mean by boundary conditions? What is happening here? What is happening here? That is at the ends of the body, no? But there is a boundary for the every surface. What is the condition prevailing there? Based on which you have to evaluate that C1 and C2 are the constants of integration. That is how the entire problem must be solved while heat generation is being dealt. Then coming to the heat generation inside a cylinder, it is a parabola. It is definitely parabola with the maximum temperature at the axis and the surface temperature. This symbol is exclusively for the heat generation, uniform heat generation. So this is the fluid temperature. What is the energy balance? Q generated is equal to Q convected from the surface of the surface, based on which you have to calculate the TW, the surface temperature of the wire, and the temperature difference. It is always given by T naught, but where would you see the maximum temperature? At the axis. That will be given by Q dot R square by 4K. So this kind of a actually, see, just try to write all the formulae in a concise manner and very precise manner, considering each topic. Say for example, if you take the conduction, the heat generation cases are 3: slab, cylinder and sphere. Just write the 3 formulae considering this, and the question is most likely to be expected, particularly in the conduction chapter. Okay, this is the temperature difference between the axis and the surface. How to get, then you may ask, how to get the surface? That is surface temperature obtained from the total heat generated. What is the total heat generated? Q dot into, this is always given for unit volume, pi r square L is equal to H into 2 pi RL. That is the convection area from the Newton's law of cooling. Because whenever you talk about the convection, what is that law that comes into mind? It is the Newton's law of cooling. Just from that, you will be calculating the wall temperature. Once you get the wall temperature, you can get the axis temperature, which is a maximum. Parabolic only. This is also parabolic. Please remember, whenever you are dealing with the heat generation in any body, the temperature distribution by default, it will be parabolic. Whether it is a slab or a cylinder or even sphere, even a solid sphere, it is also parabolic. Here the maximum temperature at the center you will see surface temperature is TWT. But here the temperature difference is Q dot R square by 6K. 6K here. Here it is 4K. It is a sphere. This is sphere, whereas that is a cylinder. Slab also I have shown. So that heat generation is a very important topic in the conduction. Then coming to the, then another important thing is the fins. Fins, when the fin cases, only remember the second case, insulated tip. That only most commonly will be asked. Only 2 formulas, square root of HPKA into T naught minus T infinity into tan HML. T naught minus T infinity into tan H, hyperbolic tan. M is the root of HP by K. Generally in the fins, most likely the things will be asked will be what is the heat transfer rate, what may be the temperature distribution, T minus T infinity by T naught minus T infinity is, no, this is hyperbolic cos function, no? Just try to remember this formula. Only for the insulated tip case only, very commonly, most likely to be asked. So the idea of this last 12 days preparation will be, you have to give a more focus to certain areas where the questions are very commonly expected in the gate. Okay, so this is the M is the root of HP by Ka, but take care of the units there. A is the profile area. A is the profile area or the cross-sectional area, and P is the perimeter, right? So from this we may get the temperature, and 2 other things are there: efficiency of the fin and the effectiveness of the fin. This is given, know that this is a tan HML by ML. Only for all these formula hold good only for the insulated tip case, where the end of the tip is not losing any heat by convection there. This is a Q with fin by Q without fin. This is also another important formula that may be asked. Q with fin by Q without fin. What is efficiency of the fin? Q actual divided by Q maximum possible. The definitions, just remember the definitions. What is actually happening? That this is actually happening. What could be the maximum possible? Maximum possible when it will happen? Only when the entire fin is at the same base temperature, at the root temperature. So the maximum possible heat transfer rate, can happen from the fin only when the entire fin is at the root temperature or the base temperature. That is when the material of the fin has got infinite thermal conductivity. Only when the conductivity of the fin material is infinity, the whole of the fin will be at the root temperature or the base temperature. Then under that condition, what is the heat transfer rate is happening is, this is the maximum possible. What is actually happening is, the material will have a finite conductivity. Under that finite conductivity case, this is actual. The ratio divided by actual and maximum possible is the efficiency of the fin, and this is the effectiveness of the fin. Both are different, okay. So these are the things that may be asked in the fins there. And above all, and most importantly, conduction, I can say in the conduction chapter, the most important topic that may be asked is the lumped heat analysis. Lumped heat analysis, where we talk about the Biot number, lumped heat analysis, where we define the Biot number should be, condition for the lumped heat analysis is Biot number should be less than 0.1. The definition of the Biot number also remember. Definition formula, and what is the definition formula? Hs by K of the solid. This is the formula for the Biot number. Lumped heat analysis is a very commonly asked question in the conduction chapter of the heat transfer subject. And what is the significance of that lumped heat analysis? No internal temperature is only a function of time. Temperature, no internal temperature gradients. No internal temperature gradients. No internal temperature differences. That is the meaning of lumped heat analysis. This is the condition. Biot number should be less than 0.1. What is the definition of the Biot number? Hs by K. But that S will be taken wisely. S will be volume by area. For the S of the sphere will be R by 3 for the spherical body. And in one of the gate examination, what is the S of the for the plate? If you just take the S of the, supposing if this is plate, thin plate, if this is L, this is the L by 2, no? That S will be the L by 2. For thin plate, which is convecting heat from both sides, and thus the S will be the L by 2. So that will be S will be selected for different geometries. So, but one thing is certain, Hs by K, as long as it is less than 0.1, there are no internal temperature gradients. That is when the Biot number is less than 0.1. Okay. Generally, that would happen when the material has got more conductivity and the convection coefficient is low, and the body is of thin shape. The small sized balls, small sized plates, slender, thin and long rods made up of a metallic conductor, automatically Biot number will be less than 0.1. A thin rods, thin cylindrical rods, small spheres, and having a more made up of a good conducting material, automatically Biot number will be less than 0.1. We don't have to calculate. But still, if you calculate also, it would be far less than the 0.1. In case if the Biot number becomes more than the 0.1, supposing if Biot number becomes more than 0.1, what to do? Then you have to bring in the very important charts called as a Heisler chart, where we talk about two different Biot numbers. Biot number and one more important number will come called as the Fourier number. So as far as the conduction is concerned, only two numbers we deal, Biot number and Fourier number. Fourier number formula will be alpha T by S square. S is a characteristic dimension, T is the time. So this Fourier number only is called as the dimensionless time. Fourier number is also known as the dimensionless one. Of course, this alpha is the thermal diffusivity given by K by rho Cp. That S must be taken very wisely. For a cylindrical rod, S is a radius. For example, this S will be for a long cylindrical rod. S you can directly take it as the radius R. And for a thin plate, it is half of the thickness. For the spherical body, if it is a radius. So what S should be there? What S should be selected? That must be validated based upon the Heisler chart. Heisler charts contains x-axis Fourier number, and these are all the reciprocals of the 1 upon Biot number. This each line will be. This is the maybe axis temperature and ambient temperature. This is the initial temperature. So this is a typical Heisler charts for a cylindrical body. This is the Fourier number. Fourier number on the x-axis, 1 upon the Biot number. Each curve will be the 1 upon the Biot number. So this is the important topics as far as the conduction is concerned. Then coming to the most easiest topic is the heat exchangers. Most easiest, only because we have only two things there. Just to revise, LMTD and NTU, that's all. But special cases, take care of the special cases. What is the special cases? In case if m dot H Cph is equal to m dot C Cpc, then this is a very important case which is very often asked in the heat exchangers, which is called as a balanced heat exchanger. Particularly balanced counterflow heat exchanger, it is a most commonly asked question, wherein you see that this is the only case where you see the temperature profiles as the straight lines. Balanced counterflow heat exchanger, what will happen there? Okay, and in case if one fluid is undergoing phase change, like for example a steam is condensing, a cooling water is getting heated up, and this is a special case. These two are the special case where the steam condensing and the cooling water cooling water is rising its temperature, where in such case, when the one fluid is undergoing phase change, it does not matter what kind of heat exchanger you are going to use, parallel flow or counter flow or a cross flow. That is a very important special case. When one fluid is undergoing phase change, it does not matter what kind of heat exchanger you are going to use, because the LMTD value is same. LMTD value is same in all the three cases: parallel flow, counter flow and cross flow. That is one important case, and this is another important case which is called as a balanced counter flow heat exchanger, where LMTD will be equal to either delta Ti or delta Te. This is a very important things. This is delta Ti is equal to delta Te only in case of that balanced counter flow heat exchanger. What is the meaning of balanced flow? Balanced counter flow, the capacity rates are equal on hot side and cold side. And again, effectiveness NTU UA by m dot Cp small. This is the one, and for this balanced counter flow heat exchanger, it will become effectiveness. In fact, that is the one important thing. Effectiveness, you have to define NTU and epsilon. Okay, actual heat transfer is already defined effectiveness, actual by maximum possible. Please revise that, actually the definitions. And for this balanced counter flow heat exchanger, the relation is given by effectiveness is equal to NTU by 1 plus NT. So these are the very important things. Just heat exchanger is a very easy question to answer in the gate. If you are seeing the question in the gate, if you are finding the heat transfer, first do that, because usually that will be easy, okay, to solve that. Because only there are two methods, either the question may come from either LMTD or NTU or effectiveness. Only two methods are there. Then coming to the slightly tough portion but a definite question, radiation. And here the most important thing is the shape factor. We don't see generally a heat transfer questions without the shape factor, view factor or configuration factor, all mean the same. Very commonly asked question, shape factor. Maybe that may be asked in any geometry, but whenever you are doing the shape factor, you have to make use of this reciprocity relation. A1 F12 is equal to A2 F21. This relation is also called as the reciprocity relation. The geometry could be anything. Actually, you may have two concentric spheres, you may have a circular plate surrounded by this thing, and are two infinitely long concentric cylinders. The geometry could be anything. Okay, or otherwise you have a hemispherical shell inside which there may be a spherical body. Okay, so the shapes could be anything, but for all of them this is a rule. But one body is completely surrounded by another body, the shape factor of the inner body with respect to the outer body is equal to 1. That point you have to remember. In all these cases, if this is 1, F12 is 1, F12 is 1 here, this is very long cylindrical, F12 is 1. Here this is 1 and this is, all this thing is 2, all this thing is 2 and F12 is 1. So you can calculate easily F21 based upon the areas. So please revise this particular, you are damn sure of getting usually one question from this. And then Wien's law and Stephen-Boltzmann law. These are the very important things you may expect in the gate regarding the radiation. Lambda m into T is equal to constant, for a black body. For a black body whose monochromatic emissive power could be indicated with respect to the lambda for three different temperatures. T3 greater than T2 greater than T1. This is a variation of the lambda m. See that lambda m, as the temperature is increasing, lambda m is getting reduced. Lambda m is the wavelength at which the EB lambda is maximum at a given temperature. Lambda m into T is equal to constant. That is a general usual question being expected in the radiation laws. And Stephen-Boltzmann law, we know EB is sigma T to the power of 4, B for the black body. See, black body, the central concept of the radiation heat transfer is black body. Black body has three characters: perfect absorber, ideal emitter and also diffusive in nature. So for the black body, all these laws were stated: Wien's law, Stephen-Boltzmann law and Planck's law of radiation. There are three laws, all are intertwined laws: Planck's law of radiation, Wien's displacement law and Stephen-Boltzmann law. All three are defined for a black body which is a perfect absorber and as well as the ideal emitter. Okay, for a black body, alpha is equal to 1 and epsilon is equal to 1. In fact, there is another law called as the Kirchhoff's law, alpha is equal to epsilon. That holds good even for a non-black body. A good absorber is always a good emitter. So that laws of radiation thoroughly try to have an understanding. And there is one more law also, Lambert's cosine law, but that is not being asked in the recent past. That is regarding the intensity of radiation, Lambert's cosine law. Right. So this is all about the radiation, and only two formulae they make for infinitely large planes. Only one formula you just remember, that is sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. If this is 1, this is 2. These are emissivities, these are temperatures. But only precaution in radiation problems is consider all the temperatures only in Kelvin. Only precaution in the radiation chapter is never write the temperatures in Celsius. This is a very commonly asked question, radiation heat flux between two infinitely large planes. And coming to that, another important radiation network actually, by using for infinitely long cylinders, if this is 1 and this is 2, this is another important case, common can be applied for any kind of situation where F12 is 1 and F21 is less than 1. F21 is less than 1. For all these situations, this formula is valid. Okay, where infinitely long concentric cylindrical surface. This is epsilon 1, this is epsilon 2, this is T1, this is T2. This formula, remember this. If that formula becomes very, very useful if A1 is far less than A2. If A1 is far less than A2, then A1 by A2 tends to 0. This epsilon 1 it goes to the upward numerator. And that means a small body kept in a large enclosure, that is this formula becomes a very useful formula. Okay. But this formula is valid for all the cases whenever these two conditions are satisfied. Remember, and then comes the radiation networks, where we define the surface resistance and space resistance. And very simple way of construction. Radiation network, construction of the radiation network is very simple if you understand the basic concept. 1 minus epsilon, this is 1 minus epsilon by 1 by A1 F1. Space resistance, only two kinds of resistances will be there. Generally, whenever you are drawing the radiation networks between whenever there are two surfaces are there, sometimes three may be given. In recent gate examinations, they have given the three surfaces. There are three surfaces exchanging heat. This is 1, this is 2, and this is 3. Just we need to, for drawing the radiation network, put one surface resistance on every surface. Between any two surfaces, you keep this space resistance. That's it. Very easy to draw the network if you have some idea about these resistances. Put one surface resistance on every surface, because the name itself suggests that surface resistance, the resistance is existing on the surface of the body. Every surface has got a surface resistance. Between any two surfaces which are exchanging heat by radiation, there will be space resistance. So give an extra attention for drawing the radiation networks. Luckily, if the body is black, the surface resistance becomes 0. Why? Because emissivity of the black body is 1. The surface resistance becomes 0. So why? Though if we are drawing the network containing this, that resistance will become 0 if the body is black. If the body is black, the surface resistance will vanish. Only space resistance will always be there. Whenever there are two surfaces are exchanging heat by radiation, there will always be a space resistance. Give some extra attention over that locality, that surface and space resistance, for calculating the radiation heat exchange between any two surfaces. Even there are more than two are there. Supposing you may ask what is the radiation heat exchange here. You have to just calculate by drawing the space resistance, what is the current passing through this. Supposing if you are asking what is the radiation heat exchange, there will be a space resistance. Just obtain that current, only that current that will indicate the radiation heat transfer happening between 2 and 3, like that. This is the space resistance. There may be a space resistance here. So the current passing here will give the net radiation heat transfer between 1 and 3. So if you understand the basic concept how to draw the networks, things will become very, very easy, because most of the parameters will keep becoming 0. Okay, so sometimes the surface resistance may become 0 because of the different reason. Supposing if the area of the surface is very large, like that of the surroundings. If the area is very infinitely large, when A is infinity, this resistance becomes 0. That is another reason for making the surface resistance 0. If you are infinitely large surroundings are there, there it doesn't have any surface resistance. The surface resistance may become 0 if the body is black again. Okay. Two different reasons this resistance may become 0. This will always be there whenever two surfaces are looking at each other. Coming to the convection there, coming to the convection here, generally people think that questions come from convection is difficult. No, actually it is other way around. It is very, very easy, provided if you have some idea how to calculate the dimensionless numbers. Here we come across the Nusselt number, Prandtl number. Most commonly asked question is Prandtl number. It is nu by alpha. This links thermal boundary layer thickness with the hydrodynamic boundary layer thickness. This is the HBl thickness. This is the thermal boundary layer thickness. Just they will ask you to calculate the Prandtl number. They will ask you. They will give the fluid. They may give the Prandtl number, or sometimes we need to calculate. You can easily calculate because Prandtl number is equal to mu Cp by K. Okay. So, what is use of Prandtl number? After calculating the Prandtl number, you must be able to judge which boundary layer is thicker, whether HBl thickness is more or thermal boundary layer thickness is more. You should be able to judge. So, that is a very, very, very commonly asked question in convection chapter in GATE. And in the recent examinations, he is asking the definition of the Nusselt number. Nusselt number is always greater than 1. Okay. And of course, this Reynolds number is there in also FM and HT there, and these numbers must be evaluated, and what geometry we are dealing, whether you are dealing with the flow over flat plates or a flow through pipes. That things will be different. The different formula will be there, whether it is a flow over flat plate or flow inside the pipes. Which one you are dealing with, that is a giveaway thing. And supposing if you want to calculate the flow over flat plate, we have a straight formula, particularly if the flow is entirely laminar. The certain formulas we have to remember. So this is for flow over flat plates. For the flow through pipes, here mostly the flow will be turbulent. Reynolds number goes above 4000. If the flow is turbulent, we have the Dittus-Boelter equation. You have to remember this formula, RE to the power of 0.8, PR to the power of N may be 0.4 or 0.3 based upon the fluid is getting cooled or heated up. So decide what kind of geometry you are dealing and what is the type of fluid. If the RE is more than 4000 means what? It is turbulent. If it is less than 2000, it is laminar. For laminar flow, it is a different formula. For 3.66, Nusselt number is equal to 3.66 and 4.36 if the flow is laminar. When it is laminar, when the Reynolds number is less than 2000. So mostly the flow will be laminar because if the Reynolds number REL is less than 5 lakhs. First step in the convection problem is check whether the flow is laminar or turbulent. If it is a flow over flat plate, calculate the Reynolds number at the trailing gauge. If it is less than 5 lakhs, you brand it as laminar. If it is more than 6 lakhs or 7 lakhs, it is turbulent. More commonly the flow will be laminar in the flat plates, in the flat plate cases. Mostly it will be turbulent in flow through pipes. Pipe flow, this is a flat plate flow. So, and recall all the dimensionless numbers, mainly 3, Reynolds, Prandtl and Nusselt, and their definitions there. And what this is a momentum diffusivity by thermal diffusivity, that is a Prandtl number definition. Recall, try to revise those numbers there, very importantly. And in the free convection, there is only one number, that is of course, that is a Grashof number, only in free convection. Revise that, free convection definition, okay. In a viscous force divided by buoyancy force, buoyancy force divided by viscous force. Some books will give it as inertia force into buoyancy force divided by viscous force whole square, but this definition is more prominent. This is a number that will replace the Reynolds number in the free convection. So, convection is all about the dimensionless numbers and the decision of laminar or turbulent and the relevant formula to apply. Okay. The very commonly asked question in the convection is regarding the Prandtl number. So, n number of times that was asked there in the Prandtl number questions there. So, this is all about the heat transfer. Coming to the another important subject, thermodynamics, TD. Thermodynamics, where the questions very oftenly come from first law of thermodynamics and second law of thermodynamics. When you talk about the first law, of thermodynamics, so whenever you are attempting the thermodynamic problem, make sure what kind of system you are dealing, whether it is a closed system or an open system, number one. what kind of working fluid you are dealing, whether it is an ideal gas like air or it is something like a pure substance like a steam or a refrigerant. The third thing is what kind of process you are dealing. Is it a reversible? Is it quasi-static? Or is it irreversible? Try to make a judgment. Sometimes you may not be aware what kind of process is there. It may not be given. So make 3 inquiries about the thermodynamic problem: nature of the system, nature of the process, and nature of the working fluid. Very luckily, most of the cases it may be air. Air is an ideal gas. When ideal gas you are dealing, what is there? Ideal gas is PV is equal to nRT or PV is equal to mRT. Okay, and this is a thermodynamic state relation is always there as long as the working fluid is ideal gas like air. Air is an ideal gas, okay, which obeys all these gas laws at all pressures and temperatures. But sometimes steam may be the working fluid, steam or a refrigerant. Then don't apply this equation because they are not the ideal gases. Refrigerant is not ideal gas, steam is not ideal gas. So the first law of thermodynamics, when you are applying the first law of thermodynamics, sometimes you will be dealing with a closed system like this, like a piston inside a cylinder. Okay, and there we write that Q minus W is equal to delta U, which is valid for any thermodynamic process. The questions in GATE may be asked, they will give one equation. They will give simply one equation. Is that equation valid for what kind of process and what kind of a system? For example, if you just write this, delta Q minus delta W is equal to du. Is it valid for any thermodynamic process? Yes. I can say my answer is yes. You can write for whether process is reversible or irreversible. And is it valid for a closed system or open system? I say it is a closed system, like a gas in a piston cylinder arrangement. Okay. So they try to write this kind of a distinguishing and sign convention. Very, very important thing is the sign convention. They give a more focus there. Heat is positive when supplied, heat is negative when rejected, like that. Okay, expansion work is positive, the compression work is negative, and give a more focus there. And this is for the equation for the closed. And when it comes to the open, again 2 things are there: steady and unsteady. Steady and unsteady. And between these two, more important is steady. Steady flow energy equation. Steady flow energy equation, SFEE. Okay, very, very commonly there n number of times the questions being asked here. Delta H plus delta KE plus. Give a more focus on this. Give a more focus on that. The steady flow energy equation. Very, very commonly that may be applied for a compressor. That may be applied for a turbine. That may be applied for a nozzle. Actually, nozzle is a very, very commonly asked regarding this. Particularly, don't forget about the nozzle. How to deal with the nozzle with this equation. And above all, throttle valve. Throttle valve. What is a throttling? Questions on throttling are very common. Throttling is an isenthalpic process where enthalpy remains constant. So what would happen to the throttling of a refrigerant, whether it gets cooled after throttling or whether it gets heated, and there one important coefficient. When you talk about the throttling, one important coefficient will come, Joule-Thomson coefficient. For ideal gas, it is 0. So like that points. For ideal gas, Joule-Thomson coefficient is 0. For the refrigerant in the VCR system, it is positive. So that questions were being asked repeatedly, and they will ask again. Mu is what is the Joule-Thomson coefficient? In the thermodynamic relations also it is important, dou T by dou P at constant H. That is in the throttling process only we talk about that Joule-Thomson coefficient. Remember this, Q minus W is delta H plus delta KE plus delta P. But here the very important precaution you have to follow is these two are in joule per kg. But fortunately or unfortunately, this enthalpy will be in kilojoule per kg. So while doing the problems, take care that maintain the proper units. Mostly you convert these two into the kilojoules because the heat transfer, work transfer, etc. may be given in kilojoules. So convert these two into the kilojoules, then you will get a correct answer. They are all defined per unit mass. Then if you want to get the power, supposing if you want to get the power there, a mass flow rate of the fluid into work done per kg, from which you will be getting the power. Maybe that is the power required for driving a compressor, or that is the power output of a turbine. Okay, turbine gives the power, right? So that first after getting the work done per kg from this SFEE, if he has given the heat transfer, sometimes you will give that adiabatic. You will the adiabatic device. The device is an adiabatic nozzle, you will get that Q is obviously 0. But sometimes it may be reversible or irreversible. You won't mention that. Sometimes fluid expands reversibly in the nozzle. Otherwise, just simply give the fluid expands. You don't know whether it is a reversible or irreversible. If it is not a reversible, don't attempt to write that PV to the power of gamma is equal to constant. This PV to the power of gamma is equal to constant is valid only for the reversible adiabatic or isoentropic process. So that precaution you have to take, that like this kind of relation, P2 by P1 whole power gamma minus 1 by gamma is equal to T2 by T1. This holds good only for the reversible adiabatic or isoentropic process, this kind of relations. This is not valid for the irreversible adiabatic, mind that. This is only valid for the reversible or frictionless adiabatic. Reversible adiabatic or frictionless adiabatic. That kind of a precaution take care, particularly when you are dealing with the nozzle, because nozzle is a very commonly asked question, because nozzle is there in every turbine, gas turbine or a steam turbine. Okay, this is one very important area. Questions are expected. Maybe question may come from the closed system or above all this unsteady. Unsteady means the filling of the flask. Supposing or emptying of the flask. Supposing there is one container will be there. There is one container, and there is a fluid passing, and that will be filling a container which is evacuated. Okay, I just opened this valve, this fluid will enter that and initially evacuated. After filling with the fluid, the pressure and temperature will be different. Now they may ask you what would be the final temperature. You will give the final pressure, you will give the pressure of the fluid in the pipe, what would be the final temperature. Give that. Please remember that unsteady state. This is quite easy also, that unsteady state. Only one equation is there, you need to remember. It may be filling of the flask or emptying of the flask. Sometimes the flask may be being emptied actually. Some fluid may be getting out, okay, through a valve. The fluid may be getting out, and what is the mass of the fluid left? You will give the initial, you will give the final. What is the mass of the fluid that has left the container? So that is regarding the energy balance. After all, first law of thermodynamics is the law of conservation of energy, which may be written for a steady or unsteady. But these two are the unsteady state situations: filling of the container or emptying the container, or fluid going out of the container. So this is all about the first law and the law of conservation of energy. Then is the above, more important than the first law is second law and entropy. All the questions of the thermodynamics, which may be weightage is around 7 marks, around 6 to 7. Heat transfer weightage is around 8 to 9. This thermodynamics will be around 6 to 7 marks. 7 marks we can say. But most of the questions will be asked either the second law or the first law and entropy. Second law and entropy comes under one. Here the main thing, second law is just revise that heat engine concept and the refrigerator concept and the heat pump. For all the devices, you have to get the thermal efficiency, COP here, how to calculate the COP, just how to calculate the COP for the heat pump. Refrigerator and heat pump both belong to the same category, obeying the Clausius statement of the second law, but based upon the useful effect, we call it as a heat pump or the refrigerator. In the heat pump, the heat rejected is the useful effect wanted. In the refrigerator, heat absorbed is the useful effect wanted. But both will require the work to be done. They are the work absorbing devices, whereas the heat engine is the heat producing device. Here we define the thermal efficiency. Of course, just recall those definitions: thermal efficiency, COP and COP there. A general definition for any refrigerator, for any heat pump, for any heat engine, we have a general definitions of efficiency and COP. In case if those machines become the Carnot, in case if they become the Carnot, you know that there is the thermal efficiency of the Carnot will be TH minus only temperatures, right? This is the reversible heat engine or Carnot heat engine. And again there is a, for a refrigerator, and again there is a COP of the Carnot refrigerator. Remember them, recall them: Carnot refrigerator, COP of the Carnot heat pump. Okay, the reversible refrigerator or the reversible heat pump, this is TL by TH minus, TL is a low temperature, TH is a high temperature. This is TH by TH minus TL. So if you add 1 to this, you will get the COP of the Carnot heat pump. COP of the Carnot refrigerator plus 1 will be the COP of the Carnot heat pump, right? So that kind of a thing. There are certain formulae which can be written for any heat engine, for any heat pump, and for any refrigerator to get their efficiency or COP. But when you talk about the Carnot machine or a reversible machine, those formulae will be in terms of temperatures mentioned only in Kelvin. Keep all these temperatures only in Kelvin. Carnot formulae all are in Kelvin only. Okay. So that distinguishing should be done, and sometimes, most of the times, they will ask a heat engine. A heat engine will be driving a refrigerator, or a heat engine driving a heat pump, because heat pump requires work, heat engine gives the work, this work will be supplied to that. So this kind of a combination problems, one machine will be driving the other. So they may ask how much heat will be required to be supplied to get this much amount of the heat rejection. Okay, then you may have to use the general definition of the efficiency of this and the COP of this. Sometimes one machine may be Carnot, either this machine or this machine, either a heat engine or a heat pump, they may be Carnot. So when the Carnot comes, you can write in terms of the temperatures, Kelvin. If it is not a Carnot, don't write in Kelvin, write only in terms of the energies. Supposing if you just take this heat pump, what is the COP of this? Q rejected divided by work. Okay. So these combinations are very commonly being asked, and sometimes you will use the word, what is the minimum work required? What is the maximum heat rejected? When you are using these words, minimum work required, or the maximum amount of work you obtainable, or that kind of a minimum or maximum words you are reading in the problem means, guess that machine may be working on Carnot cycle, because Carnot machines only are having maximum thermal efficiency if it is a heat engine, maximum COP if it is a heat pump or a refrigerator. Only Carnot machines have got the highest performance, even if it is a heat engine, or if it is a refrigerator, or if it is a heat pump. So that judgment try to give. If you are reading that minimum or maximum, think that machine may be a Carnot. So and entropy. Yes, you don't see a gate paper without a question on entropy. The change of entropy, no, that is by integrating this equation, right? This because this change of entropy will be different for different thermodynamic processes. But for calculating the change of entropy, one important relation is there for a pure substance. TdS is equal to dH minus VdP, or TdS is equal to du plus PdV. And these kind of relations you can think of to use to calculate the change of entropy. And also for ideal gas, dH is equal to Cp/dT, and du is equal to Cv/dT. So these relations we may use here to get the change of entropy by integrating, after integrating that, because they are the relations applicable for any pure substance, any thermodynamic process. Remember, these two relations, which are also called as the TdS equations, also known as the Gibbs relations, Gibbs equations, they are valid for any thermodynamic process undergone by any pure substance. Whether process is reversible or irreversible, these two equations are valid. So this kind of a technique you have to use for calculating the change of entropy. And another important thing is the Clausius inequality. Clausius inequality. Cyclic integral of delta Q by T is less than or equal to 0. Okay. Less than sign for irreversible cycle, equality sign for reversible cycle. So this round will be applicable for whether it is a clockwise cycle or anti-clockwise cycle. Clockwise cycle means what? Heat engine cycle. Anti-clockwise cycle means refrigerator or a heat pump cycle. So this Clausius inequality give a more focus, because generally you will give one machine. Maybe you will give a 3 reservoirs like this, T1, T2, T3. That machine we don't know whether a clockwise, some device is say. Okay, it may be a clockwise device or anti-clockwise device, we do not know. Okay, just give a device. First they will ask you to check whether it is a reversible device or irreversible device. You will give these heat transfers, Q1, Q2, Q3. But because they are supplied, you have to follow the sign convention. When heat is supplied, positive. When heat is rejected, negative. Then apply this relation. Plus Q1 by T1 plus Q2 by T2 minus Q3 by T3. All temperatures must be kept only in Kelvin. Dealing with entropy means Kelvin only. Like Kelvin you are putting in radiation, no? That is in the similar way we have to deal with Kelvin for this when you are dealing with entropy also. So if in case if this is 0 in the summation, that is plus q1 by t1 plus q2 by t2 minus q3 by t3, if it is 0, then you can declare it as the reversible. If it is less than 0, it is irreversible. Supposing if it is greater than 0, the device itself is not possible according to the second law of thermodynamics. This is a corollary. This is a corollary of the second law of thermodynamics. If it is 0, reversible. If it is less than 0, irreversible. Now then they ask whether that device is a heat engine or a heat pump or a refrigerator. Then the question they have to write, you have to bring in the first law. First law of thermodynamics, we know that cyclic integral of delta Q is equal to cyclic integral of delta W. In case if this is greater than 0, then declare it as a heat engine. It is a work producing device. Work is output, therefore you can declare it as a heat engine. Supposing if this is negative, that is plus Q1 plus Q2 minus Q3, if there is a negative, in the sense it is a work absorbing device, we declare it as a heat pump or refrigerator, because both heat pump and the refrigerator require work. So we have to make use of the first law to decide whether it is a heat engine or a refrigerator. Whether it is a reversible or irreversible, to decide we have to use the second law based upon this Clausius inequality, because this circle holds good both for clockwise and as well as the anti-clockwise. This is a damn sure problem generally asked in the GATE. Application of the Clausius inequality. Okay. So these are certain pockets where you have to give extra torch, extra focus while doing the last minute preparation. Clausius inequality, don't remember, and change of entropy. And the generally when you are talking about the first law for a cycle, if the cyclic integral of delta Q is greater than 0, it means that it is a heat engine cycle. If it is less than 0, it means it is a refrigerator or it may be a heat pump. So that decision, that is a law of conservation of energy. Okay. And incidentally, the area of any cycle on PV plane, say for example cycle, this area will be definitely equal to the area of the same cycle when it is put on the TS. If it is a clockwise there, if it is a clockwise here, here also it is clockwise. Clockwise means what? A cycle goes on clockwise means it is a heat engine. If the cycle goes on anti-clockwise means it is a refrigerator or the heat pump. So, but cyclic integral of PdV, like this area is the work done per cycle. This area is the heat transfer per cycle, net heat transfer. Both are equal according to the first law. So this area will be equal to this area. Judgment should be done like that. So when you are comparing when you are taking a heat engine cycle on PV and TS planes, area under any PV curve on x-axis will indicate work transfer. Area under any TS curve on x-axis indicates heat transfer, because this speaks about work, this speaks about the heat. So these are the areas for sure to get. And when you coming to the pure substances, when I say pure substances, we have to be very thorough about this two-phase diagram of a pure substance. Like this is a superheated zone, because when you talk about the pure substance, what is a very commonly thing asked? Dryness fraction. Dryness fraction X. No, for this is a wet region, this is a liquid plus vapor region. We have that certain dryness fraction. How do you define the dryness fraction? Mass of the vapor divided by mass of the liquid plus mass of the vapor. So this gap will be the H of G, latent heat, and this point will be the critical point. Most of the questions in the pure substance, they ask about the critical point. At the critical point, latent heat of vaporization is 0. H of G is also called as the latent heat. And thoroughly remember that relation, that delta S, that is between the dry saturated vapor, and this will be given by H of G divided by saturation temperature in Kelvin. This is Sg, this is Sf. Sg minus Sf is H of G by Tsat. What is that H of G? Also called as latent heat of vaporization. Okay. When you are dealing with the pure substances, we have to be very thorough with the dryness fraction, critical point, triple point. Above all, the triple point. The questions we are being asked repeatedly about the triple point. Okay, this is the fusion curve, this is the boiling curve. Like this is a solid, this is a liquid. This is a vapor. No, all the three phases coexist in equilibrium at triple point. Questions are being asked very often at the triple point. What is the significance of the triple point? At the triple point, all the three phases, solid, liquid and vapor, can coexist in thermodynamic equilibrium. Okay. And the questions being asked about the triple point, and I have solved a question also in the recent, about 10 days ago. I have given the ISRO solutions. In the very first question I have solved regarding the thermodynamics, the same question was asked in gate 21 gate regarding the triple point of ammonia. You may see that video also. I had given 10 days ago ISRO solution. There is one question regarding the triple point of ammonia in Kelvin. So there, same question they have picked up from the gate 21 question, that is where what is the triple point? Triple point is the location where all the three phases, solid ice, liquid vapor, and solid ice or liquid water and water vapor, in case of water I am talking, can coexist in thermodynamic equilibrium, and that is the reference state for measuring the properties of steam. What is the triple point of water? 0 degrees Celsius. That is selected as the reference point for measuring enthalpy and entropy of water. Please remember, enthalpy and entropy of water are 0 at 0 degrees Celsius, and both enthalpy is 0 and entropy also 0 at 0 degrees Celsius for water. All the entropy and enthalpy values are taken as a reference state, that triple point of water, that is 0 degrees Celsius. When you talk about this saturation pressure and saturation temperature, they are often asking Clausius-Clapeyron equation. Clausius-Clapeyron, that is the equation they are asking in properties of the pure substances, that is dP by dt, the variation of the saturation. This is it is given by h of g by T sat into V of g. This is a specific value. This is the Clausius-Clapeyron relation for calculating the variation of the saturation pressure with saturation temperature. For any pure substance, you remember that as the saturation pressure increases, saturation temperature also will increase. For any pure substance like water and refrigerant, as the P sat increases, T sat also will increase. So these are the very probable areas that may be asked in the gate regarding the thermodynamics. Coming to the third subject, very important subject, where the weightage may be around 7 to 8. Please give more focus for the fluid kinematics. There will be many number of questions from this. When you talk about the fluid kinematics, we have to, very first thing what we define is the streamline. Streamline, okay. What is that? What is the equation of the streamline? Given that generally, well, a flow field will be given, Vu I bar plus Vg for two-dimensional flow. They will ask you to get the equation of the streamline. You will be given that function in terms of x and y. Maybe for two-dimensional flow, you will be giving the how to calculate the equation of the streamline, and the velocity potential, stream function, okay, convective and local accelerations, ax and ay. Okay, accelerations, convective accelerations, and local accelerations. Give that more focus, that locality, okay. And the output of the FM will be maximum from the fluid kinematics in the gate examination. Okay, types of flow and continuity equation. Above all, dou u by dou x plus dou v by dou y plus dou v by dou y plus dou w by dou z is equal to 0, no? Like divergent v is equal to 0. This is the continuity equation for steady incompressible flow. Three-dimensional steady incompressible flow. This is a continuity equation. And if it is a incompressible, if it is a compressible flow, in fact it becomes rho u by dou x. That u will be the dou by dou y of rho v for two-dimensional flow plus dou rho by dou t is equal to 0 for a general unsteady compressible. It is general continuity equation. If incompressible means rho is constant. See, the recently asked added topic in fluid mechanics is compressible flow. How do you decide whether the flow is compressible or incompressible? From the important number called as the Mach number. Important number as the Mach number. That is the excuse me. As far as the FM is concerned, please give more attention for all these velocity potential, stream function, condition for irrotationality. When do you call a given fluid flow as irrotational? Okay, when it satisfies the Laplace equation, or otherwise when all the three rotation components omega x, omega y and omega z are equal to 0. Mostly they will ask the two-dimensional flows only to make the problem simple. So just check for the omega z is equal to 0. For a two-dimensional flow on xy plane, just calculate omega z, the rotation component about the z axis. If it is 0, declare that flow as irrotational, or otherwise find out the velocity potential. If it satisfies the Laplace equation, del square phi is equal to 0. Del square phi is equal to 0. This is the phi. Then the flow is irrotational. Then the flow is irrotational. So the check for irrotationality is a very commonly asked question in GATE. Okay, all the questions revolve around that equation of the stream function. If he has given the velocity potential, how to calculate the velocity of the fluid at a particular point, how to calculate the accelerations along the x and acceleration along the y direction. So that area give an extra focus. Okay, only fluid kinematics. And coming to that dynamics part, fluid dynamics part, Bernoulli, nothing more important than Bernoulli. Okay, Bernoulli's equation is a central concept in fluid dynamics. Okay, then that may be used, that may be asked how to write that. As generally, how to write it, the question may be asked like this. Supposing if it is a given like this, when you are given what is the velocity leaving, what is the discharge that is leaving, like that questions. Generally, when you are writing the Bernoulli's equation, try to select or choose the points which are open to the atmosphere. Open to the atmosphere, number one, and try to choose that point which is in a large area. Supposing if this is a large area, what is the velocity of this large area? 0. What is the Bernoulli's equation? P by W plus V square by 2G plus Z is equal to constant. Okay, when you take the open to atmosphere, then we are already aware of the pressure here, atmospheric pressure. If it is not given, take it as 101.3 kilopascal absolute. And if you are taking the another point here, open to the atmosphere, here also the pressure is atmosphere, here also the pressure is atmosphere. Therefore, many things will become easy to solve if you select those 2 points which are open to atmosphere, number one. If it is a large surface, obviously the velocity there it becomes 0. You don't have one component has become 0. So because in the Bernoulli's equation contains pressure head, velocity head and datum head. The sum of the 3 heads will be 0. The sum of these 3 heads will be equal between any 2 locations if there is no loss of head. Sometimes Bernoulli's equation may be asked like this. You will give a pipe, you will give 2 locations, and he will ask you to decide what is the direction of the flow. Generally, you have to answer that the direction of the flow is always from a location where the total head of the fluid is greater than the total head of the fluid at the other location. Supposing if the total head at one is more as compared to the total head here, that flow is like this. What is the total head here? P by W plus V square by 2G plus Z. So calculate at both the locations, decide the direction of the flow. So that kind of a thing, and similar things you will ask in the thermodynamic point of view. Now they don't give the water, they will give the steam or gas. In the thermodynamic point of view, I am talking at 2 locations you will mention some location 1, location 2. Whether the flow is from 1 to 2 or 2 to 1. It is an adiabatic device, they say, because in an adiabatic device entropy can never decrease. Regarding the entropy, the questions asked about the entropy can be very confusing and it needs critical. I can say a person who understands thoroughly about the entropy understands the whole of thermodynamics, because I can definitely say that with all my experience, a person who understands clearly about the concept of entropy, I can definitely say that he understands the whole of thermodynamics. Supposing if he has given some ideal gas, air, he has given 2 stations, station 1, station 2. He will ask you to decide, all the properties were given. He will ask you to decide whether the flow is from 1 to 2 or 2 to 1. What to do? You calculate from the given properties, we can calculate S1 minus S2. If it is calculated, if it is greater than 0, if it is greater than 0, that means it is an adiabatic device. Entropy is, the entropy will be, because S2 minus S1, if S2 minus S1 is greater than 0, yes, in an adiabatic system entropy either remains constant or it will increase. But if the S1 is greater than S2, that means in this, if the flow is happening like this, that means the flow cannot happen in this direction. If the flow is, supposing if the flow is happening in this direction, it means S2 should have to be greater than 1, or in the worst case it should be equal to 1. It cannot be less than 1. If it is less than 1 means in an adiabatic system entropy is decreasing. So the direction of the flow is decided based upon that limiting situation, that is in an adiabatic flow entropy either it will increase or remains constant. Based on that you will decide the flow is from 1 to 2. Supposing if S2 is greater than S1, yes, I can say that flow is happening from 1 to 2. If S2 is lesser than S1, if S2 is lesser than S1 means the flow will be from 2 to 1, 2 to 1 like this. So that is how we have to answer the questions there. Okay. Bernoulli's theorem, Bernoulli's equation, while you are writing, it can be asked, question may be asked from the venturimeter application or a pitot tube. Very often he is asking in the recent exams about the pitot tube. There is a water and there is you have to write the Bernoulli's equation between this location and between those location. When the water enters, you had just got the velocity head, pressure head and elevation, and you had got here the velocity is 0 because the fluid has halted there, so it has got only elevation head there. So like that. So give more focus about two important devices while applying the Bernoulli's equation, that is venturimeter and the pitot tube, which is meant for measuring the velocity. Venturimeter is for measuring the discharge. Give more little bit attention in those two devices, particularly when you are revising that. Revise Bernoulli and its applications in the form of venturimeter and pitot tube. Then coming to the incompressible flow, very important thing is incompressible flow. In the very commonly question being asked, particularly about the Reynolds number. All 5 numbers you have to remember in FM, Reynolds number, Euler number, Froude number, okay, Weber number and Mach number. All the definitions of them you should remember, okay. Euler number, inertia force by pressure force. Froude number, inertia force by gravity force. Weber number, which is the surface tension, inertia by surface. Mach number, inertia force by elastic. So if the Mach number is important in that recently added topic called compressible flow. In the compressible flow was recently added, right. So the first how to calculate the Mach number, velocity of the fluid divided by acoustic velocity, okay. This is the important number to decide whether the flow is laminar, to decide whether the flow is compressible or incompressible. If the Mach number is less than 0.3, incompressible. If the Mach number is more than 0.3, compressible. That kind of a judgment give it, because compressible flow means that number strikes in your mind is Mach number. Okay, particularly for flow through a viscous flow, more correctly viscous flow through pipes, the main thing that may ask is Darcy-Weisbach equation, head loss due to friction, FLV square by 2GD, number 1. Number 2, for any flow, if it is a laminar flow, for laminar flow there is another important equation called as Huygens-Poiseuille equation, 32 mu VL by WD square. Remember, just recall all the formula. For the laminar flow, Huygens-Poiseuille equation. It is for turbulent flow. Though this is for turbulent flow, FLV square by 2GD called as a Darcy-Weisbach equation. Many times we may write it for the laminar flow also, okay. That F is called as Darcy's friction factor. Particularly for the laminar flow, there is a relation between friction factor is equal to 64 by RE. These kind of relations, please remember, okay. And the velocity and the shear stress variation and the velocity variation. We know that it is a parabolic. This is a parabolic for the laminar flow. If it is a turbulent flow, what is that velocity distribution? Logarithmic. If it is a turbulent flow, it is a logarithmic. If it is a laminar flow, it is parabolic. That velocity distribution, no, that is 1 minus 1 by 4 mu into dou p by dou x into r square minus r square. This velocity distribution equation recall, and in each chapter there will be around 6 to 7 formulae. You just try to recall them. This is called pressure gradient. Minus dou p by dou x is called pressure gradient, which is a constant. Minus dou p by dou x, it is a constant, that is can be taken as a delta p by L, because pressure changes linearly with respect to x. Shear stress varies. That kind of a question may ask in the objective. Shear stress varies linearly in a laminar flow. Here the velocity varies parabolically in laminar flow. Velocity varies logarithmically with respect to radius at a given cross section in turbulent flow. That kind of a distributions. So, well, how do the pressure change in the direction of the flow? How do the shear stress, shear stress is a function of r, radius at a given cross section. So, that can try to recall them and try to revise them actually. This is a definitely asked questions. They were asked and they will again be asked in the viscous flow through pipes. And as far as the dimensional analysis is concerned, all the 5 numbers definitions you remember, and where to apply them. Particularly when you talk about the Mach number, we applied in the compressible flow. Okay, compressible flow is recently added topic. So they are asking compulsorily, particularly the in nozzle flow through nozzle or the diverging portion or a converging section, they are asking like this. For all these devices, there is only one answer for them equation. dA by A is equal to dV by V into m square minus 1. Okay, here the dA is positive. Here the dA is positive. Here the dA is negative. If the Mach number is less than 1 means subsonic flow. If the Mach number is more than 1 means supersonic flow. Based on which whether velocity will increase or decrease, that it can be decided. One thing is certain, according to the Bernoulli's equation, whenever there is a flow is happening, if the velocity decreases, pressure must increase. Okay, if the velocity increases, pressure must decrease. In a particular gases, I am talking in a horizontal duct. That velocity, whether it will increase with area or whether it will decrease with area, that all depends upon this equation. M is less than 1, it is a subsonic. M is greater than 1, supersonic. First decide whether they are supersonic flow or subsonic flow. And these questions may be asked again. They have very specifically mentioned flow, compressible fluid flow in the FM, and questions may come. This is the governing equation, remember. Okay. And when you come to the compressible flow, that is one important relation, stagnation temperature versus static temperature is given by this one. Stagnation temperature and T is the static temperature. Okay. So, as far as the FM is concerned, statics also should not neglect. What is the most important topic in the fluid statics? Only 2 topics, viscosity and the buoyancy. One is viscosity and how to write the buoyancy, that like writing the Archimedes principle. Viscosity, when you talk about the viscosity, you may ask like this, a block may be sliding over the viscous film, okay, a block, what is the terminal velocity of the block? Some weight will be given like this. So what is the, how to write the Newton's law of viscosity? Tau is equal to mu into dou V by dou Y, okay. So what is the velocity there? And this gap will be given, right? This gap will be given, and dynamic viscosity value will be given, or absolute velocity. Otherwise, the kinematic viscosity will be given and density will be given. Mu by rho is kV, kinematic viscosity. Mu is equal to rho into V. So this is a viscous stress based on which this is viscous stress is equal to viscous force into area. Okay, stress into area, like force into force divided by area, that will give the stress there. And that viscous force, that viscous force is the tension. You can take viscous force is the opposing force, T is the tension, and by writing the equation of motion you would be able to calculate what is the terminal velocity. In general, most of the cases this velocity variation is taken as linear. So dou E by dou Y, you can take it as the V by Y. So this is and buoyancy. Give the more attention about the buoyancy. Just how to carefully write the Archimedes principle, that is the force of buoyancy is equal to weight of the liquid displaced. And where is the center of buoyancy? And more commonly the conditions of equilibrium is asked for a floating body and for a submerged body. Separate it. You know that for a submerged body the relative positions of center of gravity and the center of buoyancy. For a floating body like a ship, how do you decide the conditions of equilibrium? The relative positions of M and G. Okay, meta-center and the center of gravity. For a submerged body it will be different, for a floating body it will be different. Very commonly the objective questions will come from that buoyancy and how to calculate the force of buoyancy and where do the center of buoyancy lie. So, these are the topics where you have to focus more in the fluid statics. Coming to the power plant, the most important thing is the Rankine cycle. And in the Rankine cycle, regeneration. Regeneration is the very commonly repeatedly being asked. Regeneration, that is the bleeding of steam, no? And the regeneration part will be very often, that is a question being asked in the regeneration, bleeding of steam. So, how much steam will be bled, how much steam will be extracted, how much steam will be extracted from the turbine required for the bleeding. So, this is the regeneration. Please give more attention for that regeneration. And how do the Rankine cycle efficiency will increase? In what way it can be improved? By providing the more superheating and by decreasing the condenser pressure. How do improve the thermal efficiency of the Rankine cycle? That is the question where they focus very often. Regeneration is a major method, prime method of improving the thermal efficiency of the Rankine cycle. Generally by rating the energy balance, by rating the mass balance for that feed water heater used in the regeneration, you can calculate how much steam, how much mass of the steam for 1 kg entering, m kg is bled, no? What will be this m value? If 1 kg is entering, how much mass of the steam should be bled or taken from the turbine, okay? So, there are 3 pressures will be given: boiling pressure, bleeding pressure and condenser pressure. This is a prime area what you get in the regarding the steam power plant, regarding the Rankine cycle. Coming to the VCR and another, because in the power plant there are 3 parts: IC, steam power plant, Rankine cycle and as well as the RNDC. In the VCR, main thing they ask about the VCR cycle, refrigeration, air conditioning, COP definition, tonnage. This is the thing they will maybe most of the questions come from the COP. Are they to produce so much of refrigeration effect, how much mass of the refrigerant is required? What is the tonnage? You will give the 1 ton is 3.5 kilowatts. You will give the tonnage capacity, that how much mass of the steam how much mass of the refrigerant must be circulated. That is one prime area in the in the VCR. Otherwise, you will give all the enthalpies. This enthalpy and this enthalpy will be different because it is a throttling process. Okay, so that area, COP definitions and the tonnage and mass flow rate of the refrigerant required. Only just to focus on that. VAR, that is never been asked in the recent past. VAR, just to know about it. VAR never asked. And air refrigeration, though that is included, that is also not asked. That is quite easy. After all, Bell-Coleman cycle or the air refrigeration cycle is just a reverse of the Breton cycle. Okay, gas turbine power plant. Because just like steam power turbine power plant, you have the gas turbine power plant, right? Analysis of the gas turbine power plant is quite easy as compared to the you just need to evaluate this Breton cycle. When you talk about the gas turbine power plant, give the focus on the Breton. And Rankine cycle, when you are analyzing, just focus upon the regeneration. How do you provide the regeneration? How much mass of the steam bled, like that? Okay. And the reverse of that Breton cycle only, it is called as the air refrigeration cycle, also known as the Bell-Coleman cycle. Okay. And that COP formula in terms of the pressure ratio, try to remember. And for this VCR cycle, vapor compression refrigeration cycle, you will be given all the enthalpies, how to calculate the enthalpy, how to calculate the mass flow rate of the refrigerant, given the tonnage. Just focus that particular domain. Okay. And in the recent past is asking particularly psychrometric relations. Only 3 relations, remember. Psychrometric relations, phi is equal to PV by PS and specific humidity is equal to 0.622 into PV by PB minus PV, and these kind of relations, that is, and and how to calculate the enthalpy of the moist air. Only three relations will be there. W into 2500 plus 1.884 into TdB. So these kind of relations, right? This is a specific humidity or humidity ratio. This is RH, and where to take these pressures, that must be very, very careful. When you are using these relations, what is PV and what is PS, they will give the data in the problem. These are the psychrometric relations. How do the psychrometric chart look like? Just give a focus on the psychrometric chart. How do the lines look like? Constant enthalpy lines, constant wet bulb temperature lines. How to read various properties on the psychrometric, just have a look at them. Okay, just for if you just spend 5 to 10 minutes on the psychrometric chart, you can easily recall that, and these three relations, and again psychrometric processes. All the psychrometric processes, just try to sensible heating, sensible cooling, cooling with dehumidification, heating with humidification, adiabatic humidification, chemical dehumidification, humidification, dehumidification, all those processes, what will happen to each psychrometric property. So you may ask like this: in a chemical dehumidification process, what will happen to the dew point temperature? This is a chemical dehumidification. Okay, this is a chemical dehumidification process. What will happen to the dew point temperature? How to locate the dew point at a given psychrometric state? At a given psychrometric state, how to record the dBT, how to record the WBT, how to record the dPT. Try to recall that. For an unsaturated air, dPT is always less than the wet bulb temperature, less than the dBT. For unsaturated air, when the relative humidity is less than 100%, the lowest is the dew point, highest is the dBT, and in between you will have the wet bulb temperature. So what will happen to the chemical dehumidification process? What will happen to the dPT? Or rather, in the adiabatic dehumidification process, what will happen to the RH value? Or rather, in an adiabatic humidification, see, this is an adiabatic humidification where the wet bulb temperature remains constant. Very commonly that is asked. Most commonly asked process in psychrometric is adiabatic humidification, or it is also called as a humidification without heat transfer. That is called as an adiabatic humidification. Very commonly asked. In that process, the wet bulb temperature remains constant, and also the enthalpy of the moist air remains constant. The main two properties remains constant during this adiabatic humidification. One is enthalpy and other is wet bulb temperature, and that process very frequently being asked in the psychrometric. Okay, and as far as the refrigerants are concerned, environment friendly, because the refrigerant which doesn't contain the chlorine, it has got a zero ozone depletion parameter, which is it won't damage that ozone layer that would doesn't contain the chlorine. Make use of that formula like R113, R134. How to write the formula? Okay, there is simple technique is there. How to write the first one is the carbon, second one is the chlorine, third one is the fluorine, and fill the remaining. First one carbon, second one hydrogen, third one is fluorine. Fill the remaining valency with chlorine. If the refrigerant has zero chlorine, automatically it's zero ozone depletion parameter it has. So the environmental friendly refrigerants, how to code them, just try to recall that. And this is one particular domain of our mechanical, which like IC. When you come to the IC engines, just talk about auto and diesel, nothing else. And dual also they are not being asked. What is the compression ratio? What is the cutoff ratio? And their thermal efficiencies. Thermal efficiency of auto, thermal efficiency of the diesel. It is only compression ratio here. Here it is a compression ratio and as well as the cutoff ratio. What engines they are being used? What is the indicated? Mainly thing is indicated mean effective pressure. They may ask the question on this. Work done per cycle divided by stroke volume. This is the indicated mean effective pressure. So number of cylinders and how to calculate the indicated power, and all about the cycles, just and easy only, very easy to answer the question given from the IC engines. And compare, they will compare for the same compression ratio or which has got the more efficiency. Definitely auto will have more efficiency than diesel, and comparison based upon the same peak pressure and temperature and for the same heat supplied. That is for different compression ratios. If you employ the different compression ratios, this has got the more efficiency than this. always in every comparison dual cycle falls in between. In both the comparisons, this is lesser than this, or this will fall in between, okay, dual combustion cycle. So that mean effective pressure, give that focus, that, and you definitely, I hope you would be able to answer every question being asked in the IC engines. But only thing is, we have to be very thorough about that thermodynamic events. Actually, there are 5 thermodynamic processes: isochoric, isobaric, isothermal, and isoentropic and polytropic. In all the 5 processes, try to recall how to calculate the work, heat, and change in internal energy. All the 5 thermodynamic processes, just try to calculate heat, work, and change in internal energy. But one thing is certain, for any thermodynamic process, delta U is equal to mCV delta T, and change of enthalpy is equal to mCP delta T, provided the working fluid is ideal gas. Okay. For any thermodynamic process, these two hold good. Okay. But if it is a polytropic process, if it is a adiabatic, or if it is isoentropic or isochoric, the value will be different. But for any thermodynamic process, as long as the working fluid is ideal gas, these two are hold good. Sometimes you will give that change for an n number of moles they will ask. They do not give the on mass basis, rather they will ask about the mole basis. Then it will be n Cp bar delta T. But how to get the Cp bar? Gamma by gamma minus 1 into universal gas constant, universal gas. This is called molar specific heat. When I put a bar, it is a molar specific heat at constant pressure. This is the universal gas constant. So sometimes you will be doing based on the mass, sometimes you will be doing based upon the number of moles. When you talk about the number of moles, you have to bring in this universal gas constant, which is same for all the gases, 8.314 kilojoule per kg mole Kelvin. And mixtures of gases, whenever you are dealing with the mixtures of gases, mixtures of ideal gases, you always write now number of moles of the mixture is equal to N1 plus N2. If there are 2 gases are being mixed, what is the final number of moles? That in a number of moles of the initial gas, and number of gas 1 plus number of moles of the second gas. And PV is equal to nRT, holds good for any ideal gas, need not be air. And that the PV is equal to nRT combined with this mass conservation, we can give all the data, we can calculate anything. Okay. When you are doing the problems, you may be writing the conservation of mass based, sometimes M1 plus M2 is equal to mass of the mixture. That is one way. Another thing is number of moles of the mixture is number of moles of the gas A plus number of moles of the gas B. That you need to use, particularly when you are dealing with the mixtures of ideal gases, as clearly mentioned in the syllabus, GATE syllabus. Okay. This is one particular domain of this, and coming to that particular second domain called as the mechanics and design part, and there the most important subject is strength of materials, SOM. Okay. When you talk about the SOM, the very important thing is the guaranteed question is principal stresses and strains. Mohr circle. That is a damn sure question, because when an element, solid element, is subjected to the normal stresses, biaxial normal stresses, and as well as the shear, that is sigma 1, this is sigma 2, two normal stresses and as well as the shear stress. How to draw the Mohr circle, and how to calculate the normal stress, and as well as the shear stress on any plane inclined at an angle of theta. Okay. This formula please remember. Okay. For how to draw the Mohr circle and what is the radius of the Mohr circle, but that will be different situations. Sometimes you will have only one biaxial, one normal stress, and we will have only one shear, like that. In such case, sigma 2 will become 0. Sometimes if this is a compressive in nature, then take this as negative and this as positive. We have a sign convention. One is tensile and other is compressive. One is positive and other will be negative. If both are tensile, give both the signs are positive, and follow the sign convention, and the shear will be there. And how to draw the Mohr circle. On the Mohr circle, all the x-axis will be the normal and y-axis will be the shear. Okay. How to construct the Mohr circle, and what do the radius of the Mohr circle indicate? The relevant questions are very important in the GATE regarding the SOM. And the easiest topic in SOM will be the first chapter, simple stresses and strains and the relations among elastic constants. Okay, simple stresses and strains and the relations among the elastic constants there. Now we have the three elas E, C, K, Young's modulus, shear modulus, bulk modulus, and Poisson's ratio. And what do we define? Lateral strain by longitudinal strain. That four elastic constants. A simple isotropic elastic material just needs only two things to be remembered, because there are relations. C is equal to 2C into 1 plus 1 by m, where 1 by m is the Poisson's ratio. Okay. E is equal to 3K into 1 minus 2 by m, where 1 by m is the 1 by, like these relations, E is equal to 9K C by 3K plus C. If you know one, you can get the all other things. If you just know the two, say, if you know the two, and all other things can be obtained. So these relations there, and thermal stresses. In the then the simple stresses and strains, there will be a thermal stress is very important, where coefficient of linear expansion, change in temperature, and in terms of these three, we will be talking about the thermal stress. Okay. Sometimes in elastic member, maybe sometimes there will be loads here, like there will be some internal forces also. There will be some internal forces. One member may be steel, other member may be aluminum, like other member like copper. So what will be the total elongation? So there are some internal forces may be acting. So the total elongation will be elongation of steel plus elongation of aluminum plus elongation of copper, and one member may be under compression and other member may be a tension. Okay, anything could happen. Okay, how to write the energy, how to write the force balance, if you by taking a section here. If you want to write the force balance for aluminum, take a section here. Left hand side forces must be equal to the right hand side forces, based on which we can decide whether it is a compression or a tension. Okay, and if it is under compression, definitely there will be a decrement in length. So the total elongation of the member will be the elongation due to the tension minus decrement due to the compression. So that this is a very easiest and prime area. And stress strain diagram. Stress strain diagram. Okay. And there only comes the proof resilience or modulus of resilience and the modulus of toughness. What is the proof resilience required? What is it? Strain energy stored, maximum strain energy stored up to the elastic limit per unit volume. And toughness, what is the meaning of toughness? Try to recall that properties. Okay, the properties of the materials, proof resilience and modulus of toughness, and what is the meaning of that strain energy. Strain energy concept is very important. Recently in 2023 also, that question asked in SOM is regarding the strain energy. Strain energy due to the self weight, he has asked that. Okay, what is the strain energy? The energy stored inside the elastic member because it is undergoing the strain. It is like a spring. You know, when you compress the spring, there is energy stored inside the spring. When you elongate the spring, when you elongate the spring, there is energy stored inside that potential energy. In a similar manner, when an elastic member undergoes a strain, there is an energy stored inside that. That is called as the strain energy. And what is the link with, what is the meaning of strain? What is the maximum strain energy stored? What is the strain energy stored per unit volume? All these things are very relevant in the SOM. Okay. And SFD, BMD, shear force and bending moment diagrams. Okay, for all the cases like cantilever, UDL, etc. And also the bending stress, bending moment equation. M by I is equal to F by Y. That equation is very important to calculate the bending stresses and the shear stresses. Okay, when the member is subjected to a pure bending. Okay, when the member is subjected to a pure bending, what are the assumptions regarding that pure bending theory actually while deriving this basic bending moment equation? And what are the how to calculate the shear stress for a different cross section, circular cross section, square cross section. So that is one thing, and of course the bending moment and bending stresses, bending and shear stresses. Okay, and torsion. Torsion is the most important thing in the SOM there. And sometimes they will ask the a stepped shaft, like this. Okay, and what is the angle out faced? That just like bending moment, you got a torsion equation. T by IP is equal to Fs by R is equal to C theta by L. Theta is the angle of twist and L is the length of the shaft and IP is the polar moment of inertia. This is the moment of inertia about the neutral axis, moment of inertia of the cross section about the neutral axis, whereas this is a polar moment of inertia, that is about the, you know, that polar moment means supposing this is the shaft cross section FZZ, about ZZ, the moment of inertia is the IP, polar moment of inertia. Okay. So that is the torsion equation, this is the bending moment equation, and as I mentioned that main focus is on the Mohr circle, principal stresses, and give that extra look at those areas, that and how to calculate the angle of twist for a shaft, and how to calculate the how do the bending stresses shape. Generally they will ask you to indicate at a given cross section how the bending stresses will be indicated like this. You will give a different formats. What is the correct format about the neutral axis? Okay. And Euler's theory of columns, the critical loading. You know, you got the 4 cases there, the critical crippling loading as such for the Euler's Euler's theory of columns there, and the slenderness ratio there regarding the columns. They are given extra focus in that. This is all regarding the strength of materials. They become the strength of materials. The main thing is main focus on the simple stresses and strains and the elastic constraints, elongations when the internal forces are there, and that is thing. And above all, the bending moments and the bending stresses for a beam, maybe a cantilever beam, and the stiffness of the beam, how to calculate the stiffness of the beam. So these relevant things, and apart from that, torsion, give extra focus there. Okay. And I am coming to this mechanics there. When the mechanics, you see, mechanics, all the topics regarding the friction, they are asking, off late they are asking very good questions regarding the friction there. Okay. And coming to the kinetics part of conservation of momentum and conservation of energy, how to make use of these two. Work energy theorem, main basically work energy, the problems on work energy theorem are very prominent in the mechanics problems. Mechanics weightage will be around 4 to 5 marks. Problems on work energy theorem as far as the kinetics part is concerned, and kinematics also will be there. They are asking to calculate the acceleration in a particular direction there. Okay, by rating the basic equations of kinematics without bothering about the forces, how to calculate the acceleration of a body along a particular direction. Okay. Usual weightage will be, give more focus to these particular topics. Okay. And when you come to the theory of machines there, the planar mechanism, no, the inversions, and that the slider crank mechanism. Okay, the type of inversions what you get there, and the degrees of freedom in terms of that is one area, and and above all, vibrations there. Vibrations is a particular domain where you can definitely expect 2 marks from that in the critical damping ratio. Okay, give the more focus in that domain of the critical damping, and that natural frequency of vibration, and when do you get the resonance. So that is the conditions where you have to focus more about regarding the vibrations there. Design is, of course, design of the welded joints, design of the riveted joints. The weightage will be around 3 to 4 marks. They may come from the either the design of the riveted joints or the welded joints, or maybe even the or in the design of the gears also. Actually, we may sometimes they may ask the questions there. And coming to that other important area called the production there, manufacturing. And casting questions will be quite easy. The most commonly asked casting question is the solidification time. As far as the casting is concerned, solidification time and the time required to fill the mold, that is another common area they may ask. And where definitely we have to write the Bernoulli's equation. Time required to fill the mold and by using the Bernoulli's equation, and of course casting defects. They give more focus to these domains in the casting there. And regarding the welding, voltage current characteristics, and voltage arc length, voltage arc length characteristics, and based upon which how much power is required, for the welding operation as such. Okay, and spot welding and the resistance welding. What is the energy? Generally, most of the times we have to use the energy conservation rule only. Most of the welding problems we may have to use the energy conservation. That heat liberated, how much power is consumed. Okay, so that is the heat flux. Which kind of a welding, because there are varieties of welding methods are there, which will heat flux, in which case the heat flux is maximum. That point, the type of weld, which kind of a type of welding requires the heat flux maximum, that you have to give a more focus in the welding. And regarding the forming, that is the forming mechanics only. Okay, the force required for the extrusion and the force required for the rolling operation. They give the yield strength. What is the force required for the rolling operation or the extrusion? Give a more focus regarding that mechanics, how to calculate the forces required for that particular rolling operation or an extrusion or for the drying. Okay, that area you give a more focus regarding the forming there. And above all, when you come to the metal cutting, most important thing is the orthogonal turning operation. Every question regarding the metal cutting, they ask about the orthogonal turning and metal cutting, and they have to definitely talk about the merchant circle diagram. This is the where the rake angle, shear plane angle, all these data need to be used in the merchant circle. Give an extra attention to this orthogonal turning question. Very often the questions being asked in the metal cutting there. Okay, particularly in the machine tools operation, in the sense particular Taylor's tool life equation. That is also very commonly asked in the metal cutting and machine tool engineering. And how much energy is required for the drilling operation, that is a very commonly question asked in the drilling, metal cutting and machine tools there. And coming to that industrial engineering part, mainly thing is industrial engineering and operation research. That inventory control, EOQ, in the inventory control deterministic model, in that economical order quantity and EOQ calculation while dealing with the deterministic model, and break-even analysis. That is the one important topic in the inventory control. As far as the operation research is concerned, give more focus on CPM and PERT, program evaluation review technique. Okay, critical path method and CPM and PERT, that is, and LPP. And just do these parts only, and apart from that, forecasting and scheduling as such. Okay. Then you may expect around 2 or 3 questions there carrying about 4 to 5 marks in the entire 4 marks you may expect here. In the entire casting, forming, welding, metal cutting, machine tools, all put together, there will be around 18 questions, 18 to 19 marks. 18 to 19 marks you may expect from the entire casting, forming, welding, metal cutting, machine tools, metrology, and above all, metrology and inspection, go, no-go gauges, and that is a very important area in metrology and metrology. And the recently added topic, NC machines, CNC machines, that also is there, automation. There may be asking at 1 mark question there, okay. But there may be, sometimes there may be evenly distributed marks, sometimes unevenly. Some topics may be given more marks. I told you, gate 22, he has asked about 12, I think 12 marks he has asked in the heat transfer, unusually higher. Generally you expect around 8. So that kind of unevenness you may get in the only rarely, but usually they try to maintain the evenness across all these subjects actually. Totally in the entire mechanical they have to adjust across the 72 to the 74 marks, okay. And don't try to learn anything new. Don't try to learn anything new. From my point of view, sincere advice, don't, in these 10 days, don't try to attempt anything. Whatever the topics most likely to be asked, I had given. In that, whatever the topics, you know it and try to brush them up. But some topics will be relatively easy. When you are reading the question paper, don't try to spend too much time on a single question. If you are finding that some questions tougher, simply jump it and go to the next question. For example, say a heat transfer. Whenever there is a heat exchanger question, immediately go there. Usually it will be easy to do it. So there are certain topics quite easy to. For example, like operation research also. That PERT problem, CPM problems, critical path method, that will be relatively easy. Try to go there. So definitely there will be one question there on that. So, try to solve the easier questions first. Thereby, you can solve more number of questions. And one very important precaution is, though you have got the correct answer, if you don't type it well, then your problem gone. Multiple choice, okay, you will see the answers. Supposing if he has asked the answer in kilopascal, but you got the answer in Pascal. If you put the Pascal answer, you got the correct answer, but that will go wrong. So what answer he has asked, what units he has asked, be careful. Particularly that problem will arise in the fluid mechanics, okay. As far as possible, try to keep all the pressures in kilopascal, okay. Then P by W, for example, pressure head is there. W will be remembering as 9.81 kilonewton per meter cube. So keep that pressure always in kilopascal so that P by W value will be getting in meters, okay. So whatever the units you are going to finally need, you are supposed to put that answer in the numerical data type. That is very important, which doesn't carry a negative marking there. Don't try too many multiple choice. Negative marking will be there. If you don't know the multiple choice, leave it. Don't try your luck. Maybe if it goes, that negative marking also will go, particularly in the multiple choice there, okay. So just on the day of examination, don't prepare anything on the day, but just relax before the day of exam. In these 10 days, you may revise whatever the topics which I told, whatever the topics you already prepared, try to revise them, try to make a small notes so that you can have a frequent reading, actually small formula and small sheets, whatever the way you feel like. And just before the day of examination, sleep coolly, have a relax in the relaxed mode, enter the examination hall. If you are feeling nervous and tense, take a deep breathing techniques you can use to relax yourself and cool, calm, stay calm, and give the examination with a full heartedness. See, if you feel the exam is tough for you, it is a tough for everyone as such. So it is only relative performance that matters. Don't give the exam very coolly with a full confidence, then the success will be yours. So with this, I am concluding actually. My name is Sekhar. I am one of the senior most faculties in the GATE, teaching this GATE for almost more than 20 years. I know which areas they will ask focus more because I keep observing the paper in the second week of February every year as such. Okay. Wish you all the best. Good luck, dear students, my dear students. Best of luck.